Hello everyone, welcome to ESE Online by ESE Engineering Academy. So today we'll see here regarding machine subject, important concepts and some questions. Here we will see the entire machines, all the parts of DC, all the parts of machines. They are transformer, induction, DC and synchronous. So I will give you here today which topics you need to concentrate more for GATE ESE, for GATE and ESE. And some important models, very few questions you will see because we need to cover all the topics. No? Now, here, first thing is, most of the students will ask how to prepare, which subject to be start first. So, in machines we have four parts, no? Transformer, induction, DC and synchronous. Out of these four, which parts or which part of machine we have to start first? So, can we start synchronous directly? Or can we start DC directly? So here the first thing you should know is a transformer topic, a transformer or DC machine you can start at any time. Okay, but you should not start synchronous machine directly. An induction machine also better to start first a transformer before that induction. Why? Because when you complete transformer first, once the transformer is completed, you will have some idea on the equivalent circuit and its operation. That will be helpful to you in the induction motors again. Same equivalent circuits will be there, same parameters will be there in induction again. Whatever we know from transformer, like in the no load operation, we have two components of current, magnetizing current, iron loss component of current. So like the same terminology you will get again in induction. So in detail you will get here. So that is helpful to you for induction motor if you start after that transformer. Like synchronous machine, directly if you see, some of the topics you will get easily in DC machine first. When compared to synchronous, there are more phasors and all, more equations, more analysis will be there in that synchronous. So if you complete first DC before that, it will helpful to you to understand well the topics for synchronous machines. Okay, so those who want to start newly from now, who want to revise also, first you revise, first you complete transformer topic and then go to induction directly also, no problem, because induction is helpful to you there after transformer, and then start DC machine and finally synchronous machines. So this is the sequence of the four topics you need to prefer for better understanding and easily understanding of the topics. Okay, first transformer, then induction, and then DC, and then synchronous machine. Okay, now let's see what are the topics we have in case of transformer first. So these are the topics. Construction first. In the construction, what you need to focus importantly is construction topic. We have two parts of construction, two parts of transformer mainly. They are transformer core and transformer winding. So from the core and winding topics, there is no numerical point of view questions directly, but theory questions only. This is important for engineering services. Engineering services we are getting questions from construction also. But for GATE point of view, we don't have any question directly from the construction of transformer core or winding. In the winding topic, little bit important is placement of winding is important. How to place winding on the core, which winding is to be placed first, LV or HV. So which is preferred to place first on the core? LV winding we prefer to place first on the core. So like that, this construction topic is most important for ESE than GATE examination. In GATE also very rarely if you get 1 mark objective question, theory question, ask there is a chance to ask. Okay, but important for ESE. Next, no load and load operation. No load and load. In the no load operation, we have two components. No load operation we are getting again phasor diagram also there. No load operation phasor diagram. So in that we have magnetizing current and iron loss current, and some of these two we call no load current, and based on that phasor diagram we can find the no load power factor angle. So this power factor angle is almost 70 to 80 degrees in the range will be there, and power factor under no load will be less than 0.5. This is under no load condition. Okay, now load operation if you see, in the load operation whenever loads are connected, flux will change in the core. The flux production will change on primary and secondary, and overall flux will remain same because the primary secondary flux gets cancelled each other at every time whenever load changes. So we call it is a constant flux device. Now in load operation again we draw some phasor diagrams for different cases, lagging power factor, leading power factor, and unity power factor. So these are important from no load and load operation. Next, EMF equation. So there are regular questions from EMF equation in transformer. We have previously in some gate exam, we have the question on mutual induced EMF, mutual inductance calculation. So this self and mutual induced EMF, regularly we have questions for gate and also ESE. For both it is important. And what is EMF equation? That everyone remember well, 4.44 phi m n f. If it is primary side we take n1, if it is secondary side we take n2. That is only difference for EMF of primary secondary. Turns only will change. Remaining equation is same. So this equation is a RMS voltage equation. EMF equation is what? RMS voltage equation it is. Okay. And what is the nature of flux included in the EMF equation? In EMF equation we have flux. What is the nature of that flux? Is it the peak value or RMS value or instantaneous value? So what is the nature of flux in EMF equation? Maximum flux it is. Remember, the EMF equation is having flux in that is maximum flux. And there are some questions on EMF equation, calculation of reluctance or calculation of, there are some questions regarding square shape core or toroidal shape of the core. So there we need to calculate what is the perimeter, that means mean radius of the core is how much. Some question is there in one of the gate exam, we have the calculation of mean radius of toroidal core or circular core. So that is we solve completely from EMF equation. So EMF equation related questions are important for both gate and ESE. Next we have losses in transformer. Losses, because it is an important topic for both engineering services and also gate, because in losses topic one of the most important loss is what? Iron loss topic. So regular questions in iron loss from hysteresis and eddy current loss calculation. Regularly we have the questions. So here you have to remember the two cases of this hysteresis and eddy current. What are that? In hysteresis loss, case 1, V by F is constant, voltage to frequency ratio constant if you take case 1. So there we have hysteresis proportional to frequency only, but eddy current proportional to frequency square. Next, in second case, that is voltage to frequency ratio not constant case. Whenever we change only voltage with frequency constant, or whenever we change only frequency with voltage constant. So in such a cases, V by F ratio is not constant, then hysteresis proportional to voltage power 1.6 and frequency power minus 0.6. And eddy current proportional to voltage square directly in case 2. So these two cases at anyhow you have to remember to solve the numericals of the two cases related. So that they are important from losses topic. Iron loss numericals only important in the losses topic for both gate and ESE. We have the questions in gate mostly for every 1 year or 2 years repeatedly we are getting questions on this iron loss. Next we have OC and SC test. Actual tests on transformer in that most important for numericals point of view for gate ESE both is OC and SC. You should be very clear of these procedures, open circuit test procedure and short circuit test procedure, very clear. What is the objectives of OC test? Why we do OC test? Why we do short circuit test? Where we prefer to do OC test and where we do short circuit test? Which winding shorted, which winding open circuited? So all these you should be clear from OC and SC test for both. Next we will get efficiency and voltage regulation, which are the performance parameters of transformer. Efficiency, voltage regulation. So both regular questions also we have from efficiency and voltage regulation in both gate and ESE. Efficiency, if you talk first, what is important in this is maximum efficiency conditions. Condition for maximum efficiency, what are that? So we have two conditions for maximum efficiency with load variation, load current variation and load power factor variation. Whenever current is changing at one of the load current, we get maximum. Where it is, we call it is X. That is percentage of load current, full load current at maximum efficiency. What is that value? It is the square root of iron loss by full load copper loss. So there we get maximum efficiency. Next, if you see, another condition is at which power factor we get maximum. That is always at unity power factor we are getting maximum efficiency. And there are some numericals related to efficiency calculation. What is the total loss at maximum efficiency, at what load efficiency maximum. Next, voltage regulation. In this voltage regulation, important means what is the maximum value of regulation, or what is the formula for regulation calculation. Percentage R cos phi plus percentage X sin phi. Regulation calculation we do know. Okay. Next, in the same voltage regulation, we have two important conditions. One is condition for zero regulation, and second, condition for maximum regulation. What is the condition for maximum? X by R ratio of load must be equated to X by R ratio of transformer. And for zero regulation, it is X by R ratio of load is reciprocal of X by R ratio of transformer. So these two conditions and numericals based on this. And in this important for objective type, particularly for engineering services questions, mostly we are getting direct formula based and some questions on regulation curve. Regulation graph is then at which power factor regulation, positive, negative, zero, all these terms. That is from voltage regulation. And after that, three phase. In the three phase transformer, there are mainly four connections we have: delta delta, star star, delta star and star delta. Now out of these, which is the most popular connection means delta star, because mostly the supply to the loads we are giving from delta star only due to availability of neutral on secondary side, single phase loads it is supported. That's why we connect, we take supply from delta star only. And there are some vector group concepts here, which type of vector group given by delta delta and star star, like 0 degree, 180 degree we get from delta delta and star star. And delta star and star delta, it is provided by what vector groups they will provide? They are providing 1 o'clock connection, 5 o'clock, 7 and 11 o'clock. So these four vector groups are in angles plus or minus 30 degrees, 180 plus or minus 30 degrees. So these are vector groups given by this delta star and star delta. So beside this, we have some special connections also in that three phase topic. They are zigzag star connections, or open delta, or SCOT connection. SCOT connection is only for engineering services. You have to prepare for objective type also, prelims, but not needed for gate exam, this SCOT connection. Okay. Next, we have parallel operation. In that, conditions important. What are the conditions to be satisfied for parallel operation of single phase transformers and three phase transformers? Okay. Next, there are numericals on parallel operation is based on two transformers sharing. If two transformers are operating in parallel and connected to a load, what is the load shared by two transformers? So that is important in this. Next, auto transformers at the last. So auto transformer is important for both gate and ESE. Definitely, majority of times if you see the previous questions, we have one question on auto transformer. One question will be there, which can be answered very easily from when compared to other topics also. So don't leave this auto transformer topic. Okay. So calculation of kVA rating of auto transformer, when we convert a two winding transformer into auto transformer, that type of questions is important from auto transformer. Okay. So kVA rating of auto transformer calculation important. Now out of these, which one we need to focus mostly for gate is, one is EMF equation, and in the losses iron loss is important. And OC test, any SC test, at anyhow you have to learn that. Why? Because some questions whatever related to efficiency, voltage regulation is there. Some questions in this, they will give some OC SC data to find voltage regulation, short circuit test required. And to find efficiency, we need both OC and SC data. That's why you should be very clear of this OC test and SC test if you want to solve these questions of efficiency and voltage regulation. So you should never leave it. Okay. Now auto transformer. So these are important, and in three-phase regular questions means we are getting questions like model of questions is they will give some input voltage, find the secondary line voltage, or they will give secondary current, they will ask primary line current. So this type of questions most of the times we have in GATE. And also for ESE. For ESE, those who are preparing for engineering services, you should prepare each and every topic in detail. There is no topic which is important for ESE. For GATE we have, but not for ESE. So you try to prepare each and every topic in detail and also solve the previous questions. Now, this is from transformer topics. Next, if you see, induction motor, induction machines. So what are important? So what are the topics first what we have in induction machine? So start first transformer and then induction machine. And induction machine again first construction will come. Construction part same for every part chapter of or every type of machine you take transformer, DC, induction, synchronous. Construction is first. Okay. So in construction of induction, we have two parts, stator, rotor. How many types of rotors we have? Two types again, squirrel cage, slip ring. And in the stator is common for both types of rotors, squirrel cage or slip ring, stator is common. And what is the stator winding we use? A three-phase distributed and short pitch winding we use in the stator, and also the three phases are preferred to connect in delta connection always. So they are delta connected. And whenever we give three-phase supply to it, RMF will develop, rotating magnetic field, which rotates at synchronous speed. And rotor is of two types, squirrel cage and slip ring type. And each one will have some advantages and disadvantages. Like squirrel cage advantage is it is very less maintenance when compared to slip ring type. Very less. Because there is copper bars inserted in the rotor slots. You no need to replace that copper bars because they never damage first. They never damage. Unlike a slip ring induction motor, we have three-phase winding and connected in star it is. And it is maintained by slip rings because through slip rings we shorted with external resistance and all to control speed of the motors or starting current of motor. We use that slip ring rotor type. Generally that slip ring induction motors we use for high starting purpose, the loads which require high starting purpose, there we use that slip ring. Otherwise, most of the induction motors we use squirrel cage type only. Okay, and in the squirrel cage, you should concentrate how to increase starting torque. How to increase starting torque of squirrel cage induction motor methods like skewing methods. Okay, how to increase starting torque. So nowadays, using drives. That is variable voltage, variable frequency drive particularly, we can increase the starting torque of induction motor also like anything, which is not provided by slip ring induction motor also. Okay, so like this we use from construction two types of rotors, squirrel cage and slip ring, and stator is common for both. Next, principle of operation. So that is very well known to everyone. Whenever supply given to induction motor, because of rotating magnetic field in that induction process means there is flux cut by the conductors to the rotor. As rotor winding is short circuited always in induction motor, EMF induce current and rotor flux, and this rotor flux will interact with the stator RMF. There is a interaction between the two fields means torque is generated, and due to the torque rotor starts rotating in same direction of RMF. And there is some relative speed concepts. What is the speed of RMF with respect to rotor? At what speed or what is the slip of the motor? And what happens if supply given to rotor with stator winding short circuited? So all these points you should focus in this principle of operation. Next, power and torque equations is the most important thing in case of induction motor, because many times GATE, ESE both we have questions on this power equation and torque equation. And which power equation mainly? Which one is if you remember with respect to rotor, we have rotor input power, rotor copper loss and rotor output power. Rotor input power. What is rotor input power? Rotor input power, also called air gap power. That is stator output, no? Stator output or rotor input, both are same. That is only we call air gap power. So if you remember, we have one relation here. Rotor input power, rotor copper loss and gross mechanical power. What is the relation of this? This is equal to 1:S:1 minus S. So from these relations, from power equations mainly, there are many times questions in this ratio itself. Rotor input to rotor copper loss, rotor input to gross power. What is the relation? So there are many times questions in GATE exam and also engineering services from this. So look at this ratio and model of questions from this also. And torque equations. Torque equation is very important to draw this torque slip characteristics also again. Because those who don't know anything about torque slip characteristics of induction motor, still you can draw the torque slip characteristics if you know torque equations well. What is the generalized or one torque equation at any slip of the motor? The torque at any slip of motor is 180 by 2 pi ns into SE2 square R2 by R2 square plus SX2 square. So this is at some slip, operating slip of the motor, some full load slip. Full load condition SFL VTEC, that is a full load torque. Starting torque means, starting torque if you want, same equation we use. Suppose starting torque required. What is the slip at starting? 1. So substitute S equal to 1 in the same equation, that is starting torque. Now it is asked to find full load torque. Same equation, full load torque, nothing but full load slip you have to take here. Full load slip how to calculate? They will give the speed of the motor. No? What is the slip of the motor? Ns minus n by ns. So that n they will give where it is rotating at full load condition. Find the full load slip and substitute here. Like that maximum torque, corresponding slip in the equation must be substituted, maximum slip. So this torque equation very important. By using this torque equation only, we will draw this torque slip characteristics. So we will draw torque slip characteristics. Now in this torque slip characteristics, you should know very well in the nature of behavior of these characteristics for variation of rotor resistance, or if supply voltage changes, how it will change, and if frequency changes, how it will change. So all these you should draw with different variations these torque slip characteristics, because they may give some torque slip characteristics to you. They will ask which variation is applied in the motor, V by F control or only voltage control or only frequency control or what variation it is. So these are all important from torque slip characteristics. For this torque equation important. Okay. Next. So this is the equation with stator impedance neglected generally, this equation. Mostly for GATE examination, we get questions from with a negligible stator impedance only, this one. But in engineering services mains particularly, objective type also we get from this equation only, prelims. But in the mains exam, we have the questions based on with stator impedance when you consider little torque equation changes. So little terms will added in that you have to focus before mains exam. Next we have tests on motor. What are the tests we conduct on induction motor? 2 tests, no load test and block rotor test. So if you have good idea of OC and SE test, these are very simple here. If you have good idea of OC test, that is no load test here, and short circuit test of transformer, that is block rotor test here. So if you have a good idea of the two, you can understand very easily this one here. Okay, but only one thing here in the no load test of induction motor, one objective is what loss we calculate from no load? Constant loss. Constant loss is sum of what again? 2 losses. What are the 2? In transformer, OC test we do to find constant loss, that is iron loss only. That is iron loss. But in induction motor, constant loss of induction motor is nothing but it is the sum of iron loss and mechanical loss. That is important here. But we don't have mechanical loss in transformer, no? Only iron loss we calculate, that is only constant loss in that. And there we use another objective, separation of iron loss into hysteresis eddy current. But here extra objective we get is we need to separate this iron loss into this constant loss into iron and mechanical loss. This is an additional objective for induction motor. We need to separate the total constant loss into iron loss and mechanical loss. For that some procedure we need to apply. That is only different here. Remaining important calculation here important is in transformer test we do on single phase. We will see generally for single phase transformers OC test and AC test. But here you are doing this test, this no load and block rotor test for induction motor. 3 phase it is. So while taking the readings, you will take the line values, line voltage you take and line current you take. The only thing is while doing calculations, you should convert that given readings to phase values first. So voltmeter reading will give line voltage, ammeter reading will give line current in this test. So that you have to convert based on connection. If it is delta connection, phase voltage equal to line, and if it is delta, line phase current is line by root 3. So we have to do calculations per phase always. But readings only we get line values that you need to observe in the test of both no load and block rotor test. Next, we have starting methods of induction motor. What are the starting methods? Tell me. Starting methods. So we have, why the starting method is required? Because generally induction motors will draw very high current at starting. Why starting current is high? Yes, we can say with 2 reasons this one. One is the load resistance behaves as a short circuit under starting condition. What is the load resistance here? R2 1 by S minus 1. Mechanical equivalent we take. R2 1 by S minus 1. Now in this, if you take starting S equal to 1, then what is that resistance will be 0. 0 resistance means it behaves as a short circuit. So under short circuit of that, or whenever that load resistance acting as 0 or short circuit, it will take high current. That is one reason. Another reason, with relative speed operation you can say, whenever supply given to motor, rotor speed 0 at that time, slip is 1, or relative speed between RMF and rotor winding is very high, which is synchronous speed, which causes high voltage. As the rotor winding shorted, high currents will flow. Okay, like this we say 2 reasons. And what are the starting methods we have? So we have DOL starting, series reactor starting, series resistor starting, and auto transformer starting, finally star delta starting. In all these starting methods, what you need to focus is, see, in the starting methods, every starting method, you have to compare the starting torque to full load torque ratio, which is IST by IFL, starting current to full load current, whole square into SFL, full load slip. So this ratio in every starting method we compare, like DOL starting or reactor starting or resistor starting or auto transformer starting and star delta starting. In all these starting methods, even the numericals also we get from this ratio itself regarding some particular starting method, auto transformer or star delta starting. So this equation we have to compare what is the variation of starting torque with respect to full load torque. Why? Because in every starting method we reduce starting current. In every starting method we are limiting starting current. So when you limit starting current, it will affect the starting torque performance, how much it changes with respect to full load torque. So that we will compare in all the methods, and based on that which method will give the good starting means auto transformer starting. Auto transformer starting will be the best starting method which consumes less power and little good starting torque. Okay, remaining when compared to other methods. So these are all important in this starting method. Next, after starting methods we have speed control methods. So for gate exam here, numericals mostly we are getting from these power equations and torque equations, and speed control methods mainly. These two topics. These two are very important for numericals of induction motor for GATE exam. But for engineering services, I am not giving it, which is important. For engineering services, when you prepare for prelims exam, you should prepare every chapter, every point in your book, you should be prepared. So for GATE only, these two are most important. And what are the speed control methods? Just recollect once. Speed control methods. So we have stator side control and we have rotor side control. So simply we have voltage control method, rotor resistance control, okay, frequency control, and pole changing techniques, and cascading of induction motors, cumulative cascading, differential cascading, and EMF injecting method. Now, which methods we can control from rotor side? Particularly for slip ring induction motor, rotor side also we can control. Not for squirrel cage, only for slip ring, rotor side also we can control the speed. What is the methods for rotor side? Rotor resistance control, externally from slip rings we connected na rotor resistance. We can change the resistance, speeds will change. Like the rotor resistance control, EMF injecting. We will inject EMF into rotor circuit through slip rings only. That is EMF injecting, rotor side there. Now voltage control, frequency control, these are all we do from stator side. Like this, in each and every speed control method, we have some conditions of load torque. Based on that, we will get numericals. That may be voltage control or resistance control, any other. So go through these conditions and then try to solve numericals of speed control methods. And finally, single phase induction motor. So here, important questions means what value of capacitor we need to add. What value of capacitor we need to add in series with auxiliary winding to get maximum starting torque. Maximum starting torque, because we use two split phase techniques, resistance split phase and capacitance split phase. Now capacitance means we need to add some capacitor. How much capacitor to be added to get maximum starting torque? So that type of questions from single phase motor we also getting regularly for GATE exam. Okay, so these are some important topics you need to focus while studying induction machines. So after induction machines, you can start which one? Not synchronous directly, you have to go to DC machines, right? Now in DC machines, what are the important topics? Let's see first. Again construction comes. Construction of DC machine. So here, like another rotating machines, you don't have only stator part, rotor part. You will have some extra parts like yoke or stator frame we call, field poles, commutator, brushes, armature core and armature windings. So all the parts individually we will see in DC machine. So go through all the parts, construction, every material important for every part of machine, and what is the purpose of that materials, okay, that is in construction. Next we have types of DC machines. Types of DC machine, you should know just how many types, and in each machine what is the KVL equations, voltage equations. Some of the voltages in the loops we take 0. So what is the KVL equations, and from the direct questions also we have. Okay. Next, in the same types of DC machine, you will get EMF equation. EMF equation. So this question is important regularly in GATE. Also ESE we have questions on EMF equation. Be thorough that how EMF related with speed and flux. What is EMF relation? EMF proportional to N phi, whether it is generator or motor, anything. If it is a generator, we take it is EG, and if it is motor, we take it is back EMF EB. Okay, so EMF equation, numericals important in this. Next will come EMF equation, that is we discussed. Next is armature reaction and commutation. So this is commutation. Till now no question from GATE directly, but we have the questions in engineering services, important for engineering services it is. And armature reaction, important for both GATE and ESE. Now this is mostly theory topic, and what type of questions we can expect from armature reaction is, during armature reaction, flux density increases at what pole tip in a generator? At what pole tip flux density increases in a generator? trailing pole tip. For motors, leading pole tip it becomes for motor. And there are some questions, methods to, what are the methods, how we increase or how we reduce the effects of armature reaction. Okay, some methods we have, no? Methods to reduce the effects of armature reaction. And what happen if brush is shifted in generator direction. And there are two MMFs we get, that is demagnetizing ampere turn and cross magnetizing ampere turn. And if you got any numerical from this also, you will get from this brush shifting concept. If brushes are shifted in generator direction, find out ATD, demagnetizing and cross magnetizing ampere turn per pole. And also some questions, compensating winding how many turns, interpole winding how many turns, or how many conductors required to compensate the reaction. So this type of questions from armature reaction you can expect. Okay. Next we have characteristics and then speed control methods. So characteristics again, generator characteristics, motor characteristics you should go. So in both generator and motor, there are some three important characteristics. Three characteristics in generator we have, and similarly in motor characteristics. So each and every generator, mainly shunt generator, series generator questions are there. Shunt generator characteristics, series generator, and compound generators. Similarly in motor also shunt, series, compound motor, mainly characteristics. Because separately we no need to draw separately excited generator, almost same as shunt generator it is. Or separately excited motor, same as almost shunt motor. Okay. Speed control methods. See, for gate point of view, this one and this EMF equation, there are regular repeated questions from EMF equation. Repeated means not same data. So model of questions are there from EMF equation and speed control methods for gate. But for engineering services, you have to go each and every point. Okay. What are the speed control methods of DC motor? Three methods: flux control, armature resistance control, and voltage control method. Out of these, flux control will give above rated speed and remaining two methods will give below rated speed. So here we have some numericals with the different conditions, with the power condition or torque condition or load torque variation with speeds proportional to speed or square root of the speed or square of the speed. So these numericals you have to go through in this speed control methods. Next, braking and starting. So this starting for gate exam you can skip this. For ESE only you have to prepare for these starting methods also. Starting, how we start with the starters, how many types of starters? Three types of starters we have: 2-point, 3-point, 4-point starter. And 2-point starter we use specifically for series motor. And braking, how many types of brakings we have electrically? Three types: dynamic, plugging method, and regenerative braking. So here objective type for prelims point of view of ESE, if you see, we get questions directly, procedures. What is the procedure for dynamic braking or plugging, and when regenerative brakes takes place, which is efficient brake out of this? So this type of questions. And losses efficiency calculation for gate. And if you go to ESE, testing part also will be there. Testing of DC machine, you have to look at testing also, those who are preparing for engineering services. So whatever topics I given here, in the same sequence you need to proceed. Same sequence. So without learning anything directly, don't go to braking topics. Whatever the sequence of topics I mentioned here, it is better to follow the same sequence so that easily you can understand one after other. These are all interlinked. Okay. So losses efficiency calculation. So we have questions in efficiency also for gate exam. So go through this. So these are the topics of DC machine you need to focus while studying, and after completion of learning, or completely if you completed the learning stage of complete machines for example, again you have to revise for the second time immediately. Just one time completed and don't keep it away. So once completed, you should revise for second time also immediately with less time whatever you taken previous. Suppose you taken to revise first time 3 days you taken. Now second time revision in 1 day you try to plan to complete this. Okay. Next we will have last one, synchronous machine. In synchronous machine, similar to previous, we get first construction. Okay, construction part. Again, stator, rotor. How many types of rotors for synchronous? Two types. What are that? Cylindrical pole and salient pole. So in this construction, we get so many important points, like particularly rotor. Stator is what? Three-phase star-connected armature winding, which is distributed and short-pitched winding, simply. So by using this distributed and short pitch windings, we can eliminate harmonics in the EMF signal. We can make EMF pure sinusoidal EMF. That's why we use stator winding is distributed and short pitched winding. Distributed and short pitched windings we use to eliminate 3, 5, 7 harmonics. So once harmonics eliminated, EMF will become sine wave there. Next, in the rotor, two types, slip ring, cylindrical rotor and salient pole rotor. Okay, two types of rotors here. And in which type of rotor we use damper bars to eliminate hunting. So these are all will come in the construction details of a rotor. Salient pole rotor will have these damper bars to eliminate hunting we use, which are placed in the pole faces and short circuited by end rings. Now these damper bars behaves like just like a squirrel cage induction motor, however copper bars we insert there. In the same way here also it will function during transient condition or hunting condition. There is a torque developed by these damper bars. Okay, so here also we get completely theory questions only from these two types of rotors, salient and cylindrical. In cylindrical rotor, how to eliminate hunting? Is there hunting in cylindrical? Yes, everywhere hunting will be there. Then how to eliminate that hunting of cylindrical rotor? For cylindrical rotor type of alternators, we don't use any damper bars. The rotor structure itself a damper bar. That will behave, that is a solid rotor, solid steel rotor, no? That will behave as a damper bar, and it is that itself will eliminate hunting whenever it takes place in alternators. That's why specially copper bars or damper bars, no need for cylindrical pole type. Okay. Next we will get armature reaction. This is the most important for synchronous machine to be understand armature reaction, because when you go to parallel operation of synchronous machines or alternators parallel operation, there each and every point, every disturbance we create and causes something reaction in that, everything depends on this armature reaction. When it is over excited, when it is under excited, you should be very clear that will come in armature reaction topic. When alternators over excite, when alternators under excite, when they are normal excite. So what is the reaction for different loads cases? Resistive load, lagging load, leading load. What reaction takes place, that you should be cleared in this. Okay. Next, voltage regulation. Voltage regulation. If you completed previous transformer voltage regulation, conceptually this is also same. Same graph, whatever you will get previously for suppose transformer you completed, then this regulation is very easy here. Like that some topics you should correlate. At each and every case you should not learn newly again. Already you learn voltage regulation in transformer. Same here also we get. Okay. In this voltage regulation again positive, negative, 0, that depends on load power factor, condition for maximum regulation, condition for 0 regulation, everything is same. But here what is important is regulation methods. We have some regulation methods. To calculate regulation we use some practical procedures. They are synchronous impedance method, also called EMF method. Next, MMF method. Next, zero power factor method, ZPF method or Portier method we call, and ESE method, American Standard Association. So these methods we use to find the voltage regulation of these alternators. So that procedures you should know well here. And remaining concept is same as the transformer topics. Next, characteristics. In alternator, we have characteristics which are useful mainly to find voltage regulation methods, that ZPF method or EMF method, whatever we use. In all these methods, we use characteristics. That characteristics you should know. What are the OCC? OCC, what is the shape? And we have short circuit characteristics, zero power factor, and compounding characteristics or load characteristics, whatever they are, you should be know the characteristics of alternators. Okay, but before these regulation methods, you should complete characteristics. Okay, first voltage regulation you go, and then start characteristics, and then voltage regulation methods. Then only you can understand that regulation methods. Without characteristics, you cannot understand, because characteristics we have to draw there. Next, power equations. That is, we have two types of alternators here: salient pole alternator power equations and cylindrical pole alternator power equations. Regular questions in these power equations of alternator. Regularly we have for gate. In the gate exam, power equation of cylindrical, power equation of salient. Both you should remember. Suppose if you see power equation of cylindrical pole with negligible RA, what is the equation? When RA neglected, then only these power equations are small one, easily we can remember also. Otherwise, when there is RA in the question, power equations will be little tough to remember, because their theta, delta, everything will come in case of power equations with RA considered. Suppose RA neglected, what is the power output of cylindrical pole alternator? EV by X sine delta. EV by X is sine delta. If it is 3 phase, 3 EV by X is sine delta we have to take. Next, what is the power equation of salient pole alternator? Power equation of cylindrical is EV by XS sine delta. What is the power equation of salient pole alternator? EV by XD sine delta plus V square by 2 into 1 by x cube minus 1 by xd. There is some equations, these are all sine 2 delta. So you have to remember all these equations. That is only the toughest thing in case of synchronous. These power equations of salient separate, cylindrical separate, EMF equation of salient is separate, and cylindrical is separate. Magnitude equations. EMF of cylindrical we have magnitude, root over that equation. And similarly salient pole EMF equation, magnitude, V cos delta plus IQRA plus IDXD. So each and everything you should remember for both salient and cylindrical. From these power equations, active power and reactive power equations also we have. So there is questions regularly from power equations. Next we get parallel operation of alternators. See, for gate exam, in this synchronous, most important is power equation and this parallel operation. After that, voltage regulation. Armature reaction is a theory topic. From there you don't get any numerical model of questions. But numerical model is from power equations and this parallel operation of alternators. Regularly there are questions. In parallel operation, there are topics like, first you need to see what is the conditions to operate alternators in parallel. Conditions. After that, two alternators operating in parallel. What is the variations in that, disturbances in that? If excitation changes, what happened? If mechanical input changes, what happened? In two alternator case. And there are some numericals also on two alternators. Next, in the parallel operation only, another topic is this alternator on infinite bus bar. Single alternator we take on the grid or bus bar. And what is its variations whenever excitation changes or whenever mechanical input changes. And in this topic only we get the V and inverted V curves. V and inverted V. So repeated questions on this V inverted V for most of the exams, for competitive exams or any other gate ESE. At the last we have here synchronous motor. So in the same sequence try to follow. In between you will get salient pole alternator sleep test and all. So everything is not mentioned. Okay. So these are the sequence of topic you should go through. Synchronous motor at the last. And again in synchronous motor you get power equations. What is the output power, mechanical power developed or input power taken by motor. With RA neglected, with RA considered. So all these equations little bit you need to remember. That is only the little toughest thing here to remember these equations. But in DC machine, you don't get that many equations. Easily you can remember. That's why DC is little easier than these topics. So no analysis much when compared to this. At the same time, no phasor diagrams and you don't get any large equations. That's why DC you can learn easily and you can do calculations also very easily, because no reactance terms there, no voltage drops due to reactance. Only resistance drop will be there and brush drop will be there. Okay. So these are the topics in each part of machines, that is transformer, induction, DC and synchronous. So whatever I given sequence, so you try to follow the sequence same while revision also. So you will get better understanding when you do your revision works. Okay. Now let's see some questions here. See this question. Read the question and try to solve simultaneously yourself and try to give the answer. Read the question. This question related to separation of iron loss into hysteresis eddy current. In OC test we use to separate iron loss into hysteresis loss and eddy current loss. First read the question. The open circuit test on a single phase 12 kVA 400 by 1000 volt 50 Hz transformer is performed using variable voltage and variable frequency source at constant V by F ratio. Okay. The following graph drawn between Wi by F and F. So there is a graph here, Wi by F, iron loss by frequency and frequency. Now you should know this procedure first. Whatever the graph we have drawn, this is a straight line not passing through origin. Wherever it touch that y-axis, this value is what? This is a, first of all, what is the iron loss equation whenever V by F ratio constant? AF plus BF square. This is the iron loss equation whenever voltage to frequency ratio constant, AF plus BF square. From this, what is Wi by F equals to A plus BF simply. Now this is the equation, Wi by F and F is drawn, which is a straight line. If you compare this with a standard form, y equal to mx plus c. Here c is nothing but constant, which is constant A. What is constant A? For that you should know what is hysteresis eddy current. This is hysteresis loss AF. This is BF square eddy current loss it is. A is the hysteresis constant, B is the eddy current constant. That AB we need to calculate. Given that if the core loss at rated voltage and frequency is 800 watts, what is the core loss at 60 Hz? This is the equation. We need to find core loss or iron loss at what frequency? 60 Hz we need to calculate. For that A into 60 plus B 60 square. Frequency is there but AB unknown. That AB we have to find from the graph. This, wherever the line touches the y-axis, that is the intercept C, or according to our equation that is A value. So A value is 10 from the graph. Now what about B value, tell me. What is B here? B value how much? Generally B is the slope there. M. What is slope? y2 minus y1 by x2 minus x1. But this is given y1, but what is this magnitude? Not mentioned. How to find B value? See this. If the core loss at rated voltage and frequency 800, no, means iron loss is 800 watts. At what frequency it is? Rated voltage and frequency means 50 Hz here. 50 Hz. This is at 50. Just you take iron loss. This is iron loss, no? Wi by F value how much? 800 divided by 50. How much we get? How much it is? 16. So Wi by F value means this value is 15. This is 15. 16. This value is 16. This value is 10. What is the change in y-axis here? 10 to 16 it increased. For what frequency here? 50 Hz. This is 50 Hz. Rated frequency. This is 0 frequency. Now you can find the slope here. What is the slope formula? y2 minus y1 by x2 minus x1. What is y2 minus y1? 16 minus 10 divided by 50 minus 0. How much it is? Calculate. 4 by 50. Calculate the B value 0.12 we get. This is B value. Now there is a value 10. A value is 10 and B value is 0.12. So once you know AB values enough, anywhere you can find the iron loss using this equation. Therefore, iron loss at 60 Hz we need to calculate. Iron loss at 60 Hertz. What is the formula? A into 60 plus B into 60 square, BF square. A value we got 10, 10 into 60 plus B value we got 0.12 into 60 square. Calculate this, we get the value of iron loss 1032 watts. Check the calculation, 1032. Okay, like this we can find iron loss at any frequency once we know the values A and B, because they are constants, they won't change further. You should know first this graph. If you don't have graph idea, you cannot solve AB here. Okay, next question. Solve this question. A three-phase delta star 20 kVA transformer 20 kVA transformer delivers rated current to load at root 3 kV. Secondary voltage given. Rated load means rated current given. So calculate rated current how much first. And the primary line current drawn from source for a transformation ratio of 0.9 is dash. Try this your one and tell the answer. How much? See here, first calculate secondary current, rated current it is supplying. No? How to find the secondary rated current? I2 equal to kVA divided by root 3 into voltage. Root 3, what is the voltage? Root 3K. What is the kVA rating? It is 20 kVA. Rated means we have to take rated kVA, 20K by 3 into K, 3K. How much it is? 20 by 3, let us take as it is, 20 by 3 amperes. This is secondary line current it is. Now what is the phase current? Which connection is there on secondary? Star. So the phase current also same, it is I2 phase is equal to 20 by 3 amperes. 20 by 3. This is secondary phase current, and given here we need to find primary line current. Given transformation ratio K equal to N2 by N1 it is. This ratio is given as 0.9. Now what we need to calculate? Primary current, phase current first. From transformation ratio everything valid for phase values only, that's why I1 phase by I2 phase. I1 phase by I2 phase is equal to how much? I1 by I2 is what? N2 by N1 only, no? Transformation ratio N2 by N1. This N2 by N1 is given 0.9. Calculate what is the primary phase current from this. I1 phase is equal to 0.9 into I2. I2 is 20 by 3. So this is 18 by 3, 6 amperes. Okay, I1 phase it is. But what is the question? Primary line current. Check which connection on primary? Delta. So in a delta, the line current is root 3 times of phase current. Root 3 into 6 root 3 amperes. How much it is? 10.39 amperes. This is the answer. But by mistake, if you written only 6 amps in the data, numerical answer type, no options. If there is 6 amperes, if you written by mistake, that is wrong only, because they are asking line current. So you have to observe all these calculations in this 3 phase, whether they are asking line, phase, and how to change phase line, that depends on connection. Delta star is given. Okay. So 10.39 amps is the answer. Next question, let's see. So this is an MSQ question it is. MSQ. Which of the following statement is or correct regarding transformer? See the options. First option, tell me which option is correct. Which option is right? First statement, first option right or wrong? Maximum regulation of a transformer can be found using short circuit test. Right or wrong it is? Yes, right it is. Because what is maximum regulation? Percentage impedance is the maximum regulation. That percentage Z we will get in short circuit test. Yes, that is correct. Next, at maximum efficiency, total loss is double the core loss. So whenever maximum efficiency we are getting, what is total loss in transformer? 2 times of iron loss, no? That is also right. Third, maximum efficiency is possible at full load UPF only. Full load UPF. See whether it is right or wrong. Maximum efficiency is possible at full load only. Full load UPF only. No. Maximum efficiency we don't get at full load. We may get at 70%, 80%, some other load. Power factor only UPF, that is okay. Maximum efficiency always at UPF, but not always at full load. So this is a wrong statement. At maximum efficiency, total loss is double the copper loss. This is also wrong. So 1 and 2, that is option A, option B. MSQ, these two are correct for this. Okay. Next. See the question on induction motor. A 10 kilowatt 3-phase 50 Hz 6-pole induction motor driving a rated load at 960 RPM. Okay. And it develops maximum torque at 750 RPM. Calculate the starting torque if rotational loss is 300 watts. Means mechanical loss given 300. We need to find starting torque and negligible stator impedance. Means you know the torque equation. Starting torque you have to calculate. If you remember, in the derivation of the torque equation, we get the starting torque. Our torque is proportional to rotor input 60 by 2 pi ns into rotor input. This is the torque relation, 60 by 2 pi ns into rotor input power. This is the torque, starting torque. Our torque relation is this. We need to find torque here. Tell me the answer from your side first. Tell me this. Starting torque how much? Very easy question. This equation you have to apply. Rotor input power you need to calculate mainly. Rotor input power. Tell me how much it is. Answer. So you take in this question, starting means again slip you have to take 1. So don't take starting. Calculate the torque just. Torque at the 960 RPM whenever it is rotating. At 960 RPM, whenever it rotates, what is the torque developed in the motor? So torque equal to rotor 60 by 2 pi ns into rotor input, same equation. Starting torque means we have to take here S equal to 1. So don't take starting, just torque developed, how much? Calculate. 60 by 2 pi ns into rotor input power. So important is rotor input calculation important here. If you remember that previous equations, rotor input divided by rotor gross power. Previously given, no? What is that relation? 1 is to S is to 1 minus S. Rotor input by rotor gross power is 1 divided by 1 minus S. Okay, what is slip here? Calculate. It is rotating at 960 RPM, slip equal to ns minus n by ns. How many poles are there in this? 6 pole. The synchronous speed is 1000 for that, 1000 minus, it is rotating at 960 divided by ns minus n by ns it is. How much? 0.04. This is the slip. At this speed it is rotating. At some load condition it is. That's why it is not taken starting. Not starting, it is just torque at some load condition. Whenever it rotates at 960 RPM, this is the slip of the motor. Next. Substitute here. Rotor input is unknown for us. This is equal to, how to find gross power again? This is also important. Gross power, how to calculate? Gross. See, it is given 10 kilowatt. It is driving a rated load, means full load we have to consider 10 kilowatt. What is the 10 kilowatt in the question? The power rating always indicated is net mechanical power or net output of motor. So, gross power equal to net power plus mechanical loss, rotational loss. net power is 10 kilowatt plus what is the mechanical loss given rotational? 300 watts it is. Now it is 10.3 kilowatts. This is what gross power. Gross power is 10.3. Now calculate from this rotor input power. This is rotor input. P in means rotor input. How much it is? P gross 10.3 K divided by 1 minus S. What is the slip of the motor? 0.04 under this condition. How much it is? Rotor input power. Check it. Rotor input, how much? Okay, 10.729 kilowatts. This is the rotor input power, right? Now substitute in this equation, we get 60 by torque equal to 60 by 2 pi ns. Ns is 1000 rpm. Rotor input we got how much? 10.729 kilowatt into 10 cube. Calculate this, we get the starting torque. Not starting, it is strike out in the question also starting, because it is running at some condition. So at that time we have to find out the torque. Otherwise if it is starting torque, you have to take S equal to 1, rotor input power equation. So here you have to substitute S is 1. Okay, starting torque will be there, but depends on S equal to 1 it is. I am not taking that S equal to 1 because it is running at some speed, driving a load, no? So at that speed, what is the slip calculated and find out the torque. How much? Yes, it is coming 102.4 Newton meters. Check all of you this. This is the torque developed at this rated condition whenever it delivers rated output power. 102.4. That is option A is correct. Next question. See this question. This is on DC machine. Look at this. A 4-pole wave connected 250 volt DC shunt generator has 500 conductors. The field resistance 50 ohms. When it is supplying a load of 100 amperes, the brushes are given a lead of how much? 10 degrees electrical given. Calculate extra field turns required to neutralize effect of demagnetization. First of all, whenever brushes shifted, no? So here direction not mentioned means always you have to take generator direction only. Whenever brushes are shifted, we get extra effect is demagnetizing effect. Extra demagnetizing. So whenever there is extra demagnetizing, they are asking what are the extra field turns. When there is a demagnetized, some flux drops. To compensate that or to neutralize that, how many extra field turns required in the field winding? That is the question. So first what you need to find, as brush is shifted by 10 degrees, you calculate how much demagnetizing first. Okay, calculate ATD per pole. Demagnetizing ampere turn per pole equal to, what is the formula for this? 2 theta by 180 into ZIA by 2AP. ZIA by 2AP. What is theta? 10 degrees. And what is IA here? See, field resistance given 50. It is supplying load current of 100. Then IA in case of shunt generator is IL plus ISH. Okay, what is IL? 100. What is ISH? V by RSH. Voltage is 250 by 50, 5 amperes. 105 amperes is IA. Now substitute here. 2 theta. Theta is 10 degrees divided by 180. Z, how many conductors are there total? 500 conductors into armature current 105 divided by 2 AP. What is A here? Wave connected A equal to 2 and poles are 4. 2 into 4. Find out how much demagnetizing. Demagnetizing. Check, it is coming 364. You have to check, cross verify the values. 58 amperes. Okay, 364.58 ampere turn per pole it is. Ampere turn per pole. So this much ampere turn is extra demagnetizing it is. This is demagnetizing. So because of that flux drops, then we need to add some extra turns in field winding to neutralize this. That means Whatever demagnetizing is there, that is extra we have to compensate, we have to generate that. Therefore, the number of turns in field winding let n and current in the field winding same. Even if you add any number of turns, same current only will flow. This must be neutralized by this much again extra. The MMF required is this much, 364, whatever demagnetizes, 364.58. And what is the current passing through field winding now also after placing extra turns? Let extra turns are n. Same current will pass 5 amperes only. This is equal to 364.58. Now solve from this, number of turns required additional is 72.9 or approximately 73 turns required for us. 73 turns required in order to neutralize this extra demagnetizing effect of 73. Option B is correct. Okay. Let's see a last question. So this is on alternator taken from parallel operation. During synchronization process we use lamp methods, so that is related. This is MSQ model. Read the question first. A three-phase alternator is to be synchronized with a bus bar having phase sequence RYB. Okay. Using lamp methods, if three lamps L1, L2, L3 are connected as shown in figure, and it is observed that all lamps are dark at a same time. All the lamps dark at a time. Not like one is first dark, after some time other dark, not like that. All are dark at a time. And flickering at 30 flickers per minute. Means frequency difference is there. Frequency difference is there, no doubt. Okay, per minute. Then which of the following are correct? Now you see the options and figure. So L1 connected between RR dash, YY dash, L2, BB dash, L3. Okay, L3 connected between BB dash. Now according to this statement given, the lamps, it is observed that all the lamps are dark at same time. Means RR dash in phase, YY dash in phase, BB dash in phase at same time, because dark at same time means what is the voltage difference here? 0. Suppose RR dash in phase, YY dash also in phase at same time, BB dash also in phase at same time. That's why lamps are dark at that time. Okay. So means phase sequence for same, for both same or not? Yes, phase sequence is same for both. RYB, this is also RYB sequence. Same sequence is there, but frequency different. That's why it is flickering given. 30 flickers per minute means there is some difference in the frequency of bus bar and alternator. Now, which option is correct? Bus bar and alternator both have same sequence or not? Yes, same sequence only. That's why at a time all are dark. Otherwise at a time they won't be dark. Okay. Next, bus bar frequency more than alternator. Right or wrong? And third statement, bus bar and alternator have different sequence. Not different, because if their sequence is same, then only we get at a time all are dark like this. This is, let RYB, bus bar, 3 phases, and R dash, alternator 3 phases, R dash, Y dash, B dash. This is Y dash, this is B dash. If all are in phase, having same sequence, then only all 3 lamps are dark at a time. Okay, and they will become bright also at a time. Only dark is mentioned here, bright also they will become. Frequency difference, no. With the different speeds they are moving inside. But sequence is same. Now, bus bar and alternator have same sequence, this is correct. Next, second, bus bar frequency more than alternator. And fourth, bus bar frequency less than alternator. What about these 2 points? Second is right or wrong? Yes, frequency different is there, but we don't know which is more, which is less. Any case, whether bus bar frequency more than alternator or bus bar frequency less than alternator, in both cases you will get that flickering. We cannot identify that here directly. That's why this B and D also correct. So as it is MSQ I said, more than one option also right. That is what? A, B, D. So A, B, D. These 3 options are correct for this. Okay. So this is from parallel operation of alternator with the synchronization process, synchronization of lamps. During that we connect lamps, no, like this. So there are some methods also. So these methods, in previous one of the gate also we have questions on these lamp methods. same as it is with little slight changes in the question. So this is our today's topic. So briefly I given some topics idea and some questions, model of questions how we get for GATE ESE. Okay, so all the best.